Process Explorer is probably the most well-known tool in the Sysinternals suite. Hi, my name is Pavel, and I want to do a quick deep dive into Process Explorer, see what it can do, and most importantly, how to understand and what the information it provides actually means. So I'm a developer, trainer, and author, and apparently a speaker as well. And in fact, I've been part of the Sysinternals team for the last 9 months or so. So if you see any new bugs appearing in recent tools, it's probably on me. And I've been writing a few books recently. You can find all that information online if you're interested. So normally people think of Process Explorer as a super task manager, because Task Manager also shows process information, but Process Explorer shows much more information, much greater detail than Task Manager ever could. In this screenshot, you see the current Process Explorer on the left and some enhancement I'll show you today on the right. So what is Process Explorer? Its main feature is to show dynamic information about the running system. This is mostly about processes. I mean, it is called Process Explorer for a reason. So it shows information about processes and whatever is contained within these processes, such as threads, modules, handles, TCP connections, and lots of other stuff. It also shows information about kernel objects while we view handles in the particular process of interest, and I'll show you that as well. It has some global information about the system, such as CPU usage, memory, I/O networking, and so on. Some of the information is textual. In fact, most of it is textual, but there are some graphs that allow you to see some things as they pass through time, as they change through time, such as CPU utilization, memory utilization, and so on a system-wide basis or on a process basis. There's also a set of operations you can do on processes. Well, first you can kill processes, but then there are other stuff you can do with processes, such as suspend them and view other information about threads and also perhaps suspend them as well. You can also close handles, which might come in handy from time to time. One thing that Process Explorer also does very well is allow us to search for interesting objects across the system. So this could be files, it could be other named objects such as mutexes, semaphores, and other types of objects Windows supports. That's kind of the basic overview, but really what we want to do is look at Process Explorer itself. So let's go to Process Explorer. Here is Process Explorer. When you open Process Explorer for the first time, it looks something like this. You have a tree-like view of processes, and then for each process, you get these various columns. So these are just some of the columns that are available. If you want more, you can right-click, go to Select Columns, and then you get a very big list of columns divided to various categories to make it a bit easier to find what you're looking for. Now, first consider this tree-like data structure. What does that really mean? If I go ahead and double-click one of these processes, you can see in the Image tab, it talks about the parent of the process. So the parent of this particular process is SVC host with the process ID 1444, which happens to be exactly this one as it's shown here in the tree. Here's 1444. Of course, we can move columns around if we want them to be in a different location. So it talks about and shows the parent of that process. Now, for some processes, it seems that they're completely left justified. It seems like they don't have a parent. So let's take a quick example, such as a WinLogon here. So if I go ahead and double-click WinLogon, apparently WinLogon doesn't have a parent process. It's a non-existent process which has the ID 1216. So in fact, it was the process ID of that process, but no other information is available for that process because that process is now gone. And the parent process ID is stored in the child process ID. Now, it's important to understand in Windows that there is no parent-child relationship in terms of any kind of dependency, which means that if process A creates process B and process A dies, process B is completely unaffected. So we have this process which doesn't have a parent. What about this ID, however? Can a new process be created that has the same ID? The answer is yes. Process IDs are not unique throughout the lifetime of a system. They're only unique as long as the process is alive. However, Process Explorer is not confused. if it has another process called 1216 that has since been created, Process Explorer also compares the start time of that process. If the start time is after our current process, then surely it can't be the parent process for that process. And so process doesn't get confused and will still show non-existent process for that particular case. So the question who created who is sometimes interesting to understand how things get created. And that's what the tree-like structure shows us. If you want to sort in a normal way, you can simply go ahead and sort from A to Z or Z to A. The other thing that is fairly obvious in Process Explorer are these colors. So these colors not for making Process Explorer pretty, although that might be a good reason for having them, but for each color there is some significant aspect that is part of the process in question. So let's see a few examples. One of them is this yellowish process. So yellowish processes are for .NET. It means that that particular process is hosting the CLR, the .NET runtime. And when you double-click or look at the properties for that process, you'll find that there are two tabs here. One of them is called .NET Assemblies, which shows all the .NET assemblies loaded into the application domains of this process. And there is a .NET Performance tab here that shows some performance counters that you can find in usually using other tools such as Performance Monitor. And this is the .NET CLR memory category, but there are other categories here which are also related to .NET. So for other types of processes that don't host the CLR, you will not see these tabs in the properties. These are contextual tabs. They only exist for .NET processes. Let's take another color as an example. We have this pinkish color. So this pinkish color is for services. And just like with .NET, there is a special tab in that particular case called Services. So you see that in this particular example, I've double-clicked an executable which is hosting a single service right here. And in fact, it is implemented as an executable, which normal processes have to be implemented in this way. However, if you're familiar with Windows, you probably are very familiar with this thing called SVC host. And this SVC host thing is a generic host for services that Windows uses for most of its services coming out of the box. If I double-click any one of those, we'll see the Services tab existing in that properties, but then you'll notice that the actual implementation is for services in a DLL, which makes sense because we have a generic executable, a generic process to host services, so the particular detail of the specific service has to be coming from somewhere else, which is that DLL. And in today's systems, you'll find that most services are actually hosted in their own process. You can see there are many SVC host instances here flying around. There's one perhaps that is a bit different, and it's hosting multiple services. One of them is very important. That would be the DCOM launch service, which is critical to Windows, in fact, and Windows can't really function without it. It has some very important responsibilities. So the ability to host multiple services in a single process, this is the thing that is using these DLLs for. So the ability to have services implemented as DLLs allows us to load multiple services into the same process. And previously, before Windows 10 version 17.03, there was some form of segregation where you had multiple services in a single process to conserve processes, to conserve system resources. However, starting with version 17.03 of Windows 10, if the system has at least 3.5 gigabytes of RAM, for standard systems, that's probably not an issue, but could be an issue for IoT devices or Windows Phone and such small devices, then most services get their own process. And this is for robustness and stability. So if one service crashes, it brings down its process, and the only service that is affected is that process. On the other hand, if you have multiple services in the same process, one service causes some exception, then the entire process shuts down, causing all the other services, which are not to blame, to crash as well. So pink processes are about services that are hosted in that particular executable, that particular process, to be more precise. And then we have these cyan color. So this cyan color is mostly used for UWP processes. So for example, I have a calculator here running, and if you go ahead and look out for calculator, you'll see that it has this cyan color. So these are applications that are usually using the Windows runtime, and they have some extra management on top of them. For example, if I go ahead and minimize calculator now, you'll notice that the process becomes suspended and changes color to the suspended color if I enable that color, which means that all the threads in the process have now been suspended and nothing can happen in calculator. Once I restore calculator, its process goes back to life and it can continue doing its calculator thing. And so most cyan processes you'll find are these kinds of processes, but it's not precise. So for example, if you go ahead and look at Explorer, you'll find that Explorer also has this cyan color. Does that mean that Windows Explorer can be minimized, causing it to be suspended? The answer is no. And the cyan color really is about hosting the Windows runtime, using Windows runtime APIs. Behind the scenes, there's a function, isImmersiveProcess, which is the one that's actually being used by ProcExp to determine whether to color a process with cyan color. And so Explorer is definitely not a UWP application, but it is using Windows runtime APIs, and that's why we get that color. You also find many processes of type runtime broker, which are helpers, UWP processes that allow them to do certain operations which they cannot do on their own. And that's because UWP processes run inside something called an application container or app container. You can see that in the integrity column here. And container means, among other things, very low power, in the sense that you can't access resources or objects that have a medium integrity level or higher in any invasive way. App container really means low integrity level. So integrity level is another very interesting aspect of Windows security, but unfortunately we don't really have time to discuss that. So we have these colors, and let me talk about maybe one or two other colors. So we have this particular color. This is a color called fuchsia. This is the default here for protected processes. So protected processes can't be accessed invasively from user mode regardless of the user's powers. So even if the user is administrator or has any crazy privileges, it doesn't matter. You can only get very shallow information about a protected process, whether that's protected with the classic protection from Vista or the protected process Lite, which is the enhanced protection, or more, I would say, flexible protection module from Windows 8.1 and later. You can figure that out using that protection column. So if I want, I can even sort here by protection. You can see the various protection values that you have here. And these are based on the signer and the level of the signer. So some signers are more powerful than others. And there's these two modules, the classic protected module and the protected light module. And so this is the fuchsia color. And by default, you will not see that color because it is not enabled by default. So you can go to Options, Configure Colors, and then enable that color if you wish. So I've enabled most of the colors except for jobs. We can do that as well. And in that case, we'll find that many processes get colored with that brownish color. These are processes that are part of a job. And just like with other cases, when I double click one of these, we get another contextual tab here, which is the Job tab. And the Job tab shows all the processes that are part of that job. In this particular case, I've selected one of the instances of WMI per VSE, which is the WMI worker process or worker executable, which we have multiple instances running. And we can see that there are some limitations on that job. So the purpose of a job in general is to manage a set of processes as a unit, providing some form of limitations or limits to these processes. So you can see here some limits so that WMI service request and operations that are going to happen because of that request will not consume too much system resources. So for instance, the job cannot consume more than 1 GB of memory. A number of processors cannot go beyond 32. So ProcExp shows you the limits that a job has. So again, this tab is contextual and will not appear for processes that are not part of a job. So these are some of the colors you can find ProcExp, and as we've seen, you can configure those to see them or not see them based on your preferences. And so other than that, the important part that we see in ProcExp is that it has a lower pane. So you can show that lower pane by clicking some toolbar button or using the Ctrl-L shortcut. And once you do that, what you get is a pane here at the bottom that now contains 3 tabs for handles, modules, and threads. This is a new feature in ProcExp. Previously, you had only modules or handles, and you could switch between them. But now we have some tabs here which you can switch between and show threads also, not just modules or handles. So any process you select here, doesn't really matter which process that is, you get the view changing based on your selection. And of course, you can sort any one of these columns in terms of threads here, and even perform some operations such as looking at the call stack, the module, maybe even terminate the process, and the thread, and suspend the thread as well if this is what you want. And of course, we can switch to the modules view to see all the modules that are currently loaded into the process address space, seeing the name, description, path, and the base address and image base. So the base address is where the DLL is actually loaded, and image base is where the DLL would have liked to be loaded. And if these things are not the same, it means that the DLL has gone through a relocation process. And this is also marked in this yellowish color right here. So you can see here that the numbers here are different, which means that this particular DLL had to be relocated because its preferred address was already taken. So you can see here a list of properties for DLLs. And of course, this is just a partial list of columns. You can right-click, you get to the DLL columns. You can select other columns you would like to see, because by default, you actually don't see some of the columns I'm showing here. And then we have the Handles tab. So the Handles tab is about showing us all the handles that are part of the handle table of the process. We know that every process has its own handle table, and these handles point to various kernel objects. In fact, most of the functionality in Windows is provided through kernel objects. And so if you want to do stuff, for example, you want to open a file, you have to obtain a handle to a file object that represents the connection to the file you would like to talk to. And without a handle, you can't really talk to the file. And so these handles are just numbers that are indices into some tables which are in kernel space, but you can see the numbers right here. And you need to remember that every handle table is private to the process. So if I have a handle here to some registry key with the value 78x, I can't just pass along that number to a different process. That doesn't make any sense, because the other process has its own handle table where 78 points to a completely different object, or maybe to nothing. And so it's important to realize handles are private to a process. So again, when you just start up ProcExp for the first time, you just see the type and name columns, but you can right-click as always and show more columns for looking at handles. So you can see the handle value, and the first handle which is valid has the value of 4. 0 is never a valid handle value. You can see the type of object, and Windows has many types of objects, some of which we understand very well because we can use them and we see them all the time, such as processes and threads and registry keys and files and so on. Some of them perhaps not so much because they're more internal, and some of them in fact are completely undocumented. Here you can see the name of the object, and this is kind of a tricky column. It's not really the name of the object in all cases, but it is some form of name that makes it easy for us to understand some more details about the object that is pointed to by that handle. I'll say a few more things about that in just a moment. Then we have the access mask here. The access mask is a set of bits indicating what is the power of that handle. So I might have multiple handles to the same object. It doesn't mean that all these handles are the same. Each handle has its own power. And so that power is represented by the access mask. For instance, this registry key has the access mask to 0019, and in order to understand what that really means, we have to go to the Windows SDK documentation to figure out what each of these bits mean, or we can just look at the decoded access column, which tries to interpret that value in a human readable way. So essentially, we can see here that this handle can do read operations from that registry key, which means that if it tries to do something like a write operation for that key, that would fail with access denied. So not all handles are born the same. Same goes for every other handle you see here. And then we have the object address. The object address is where the real object is in kernel space. You can see here that the address is a very big number, which is what we expect on a 64-bit system, because the kernel space starts at the upper 128 terabytes of address space. So this is somewhere inside that address space. What can you do with that address? Well, onto itself, nothing. From user mode, that information is practically useless. But if you're doing some kernel debugging or have a kernel debugger available to you, you can actually use that address to gain more information about the object by looking at it through the kernel debugger. So for instance, if I go ahead and double click one of these handles, what we see here are properties for the object. So notice the properties are for the object, not for the handle. The properties of the handle itself is just represented here by this line, which means that if I double click two handles that point to the same object, I'll see the exact same information, because this is about the object, not about the handle. And so you can see the name of the object, the type, some description. Here's the address again where the object is in kernel space. We can see here number of handles that are open to this object, currently just one. And then we have references, which is kind of weird because it's supposed to give us the total reference count of an object. Kernel objects are managed with the reference count, and only when the reference count goes to 0, only then the object is destroyed. However, if you look at Windows 8.1 and later, the reference count seems like something that doesn't really make much sense. I mean, could there really be 65,000 something kernel clients holding pointers to the object or something like that? It is unlikely. So in fact, this number combines a usage for the handle. So to actually see what it really means, ProcExp in this case falls short. There's no way to get that information from user mode very easily. We can go to a kernel debugger just for fun and just use the object command with that address. And then we get the information about the fact this is a registry key, and you see the same pointer count or something a bit different because it is based on usage. You can click that, and then you get the trueref command, which will show you the real reference count for this object. So it takes a couple of seconds to figure this thing out, but eventually we'll get the actual result. So this is something we can't get from ProcExp because it doesn't have the full view of what is going on in the kernel. However, in the meantime, one thing I did wanted to show in terms of modules before I forget, if I go to something like CSRSS, which is a protected process, notice we see the list of modules and DLLs inside this process. If you've used previous versions of ProcExp, you wouldn't see that information. But now we do, and that's because we use the ProcExp driver, assuming you're running ProcExp with admin privileges, to open a powerful handle to the process and circumvent the limitation we get from user mode, not being able to access invasively protected processes, but now we can because we leverage the power of the kernel. So now all protected processes do have a list of modules, and the list is not empty as you might find in previous versions of Process Explorer. So back to handles, here's the actual pointer count, that would be 1. So the reference count in 1 is 1, which means this is the only handle and the pointer to the object. So back to handles here, one of the perhaps trickiest parts here is understanding the role of name. In fact, when you think of the list that you see here, is this the entire list of handles in the process? So not really. This only shows named object as far as ProcExp is concerned. To see the true list of all the handles in the process, we have to go to the View menu and select here Show Unnamed Handles and Mappings. Once we do that, we see that the list is greatly extended. Now we have many more handles than we previously saw in the process, and that is truly the full handle table for the process. You notice that handle number 4 does really exist, and number 8 exists as well. These are just for objects that don't have names, which are just normal objects just like anyone else. They just don't have names, which is fine. A name is definitely not mandatory, and some object types, in fact, can't have names anyway. So this is fine. Previously, we've seen 34 as the first handle, but in fact, it is not the first handle. So back to named objects only, I want to focus on names a little bit. So these names are not really that trivial to understand. Some objects are truly named. They do have names. For example, sections have names, events have names, semaphores and mutexes have names, and these are true names, which means we can open the object by name using an appropriate API. However, some objects here that seem to have a name don't really have a name. So let's look at some examples. One of them is process. So processes don't really have names. Processes have IDs. However, ProcExplorer shows us a name for the process because it is just useful to see that information, but it is not a true name. This is a process ID, of course, but it shows us as a named object. Same goes for threads. Threads also don't really have names. They have IDs. So you can see here that this particular handle points to a thread inside the Explorer itself, and that would be the thread ID, which of course is something that might be useful information for us, but it is not a named object. So you might be familiar with the feature introduced in Windows 10 where you can actually give a description to a thread using the setThreadDescription API. And so you can associate a string with the thread, but it is not a thread name. It doesn't have to be unique, and there's no way to look up a thread based on that description. In fact, it is mostly used for debugging purposes. Visual Studio can show the description of a thread, for example, that could help you identify interesting threads in your application. So these are not named objects. Another type of object which is not named are keys. Registry keys don't really have names. This might seem very odd. What do you mean you don't have a name? Here is a name, but no, this is just a path pointing to registry key. The object itself doesn't really have a name. And the most confusing aspect is definitely files. So file objects really don't have names, which seems really, really odd. I mean, what do you mean they don't have names? Isn't that a name for a file or a directory? So yes, this is a path, but it is not the name of the file object. This is not really about files. File objects are a way to contact or to communicate with devices, where files in the file system are just one particular case. And to prove that, there is another tool I would like to briefly show you, which is WinObj. WinObj is another Sysinternals tool that shows us all the named objects in the system, all the truly named objects in the system. And they are managed in this kind of hierarchical manner. Let me run this with admin privileges so that we can see everything. And so you can see various types of objects here, such as events and semaphores. In fact, under sessions 1 and base named objects, you'll find all the named objects created by processes in session 1. So I dare you to find here a file. You won't find a file here. You won't find a registry key. You can search, but you won't find anything like that. This is kind of a proof that file objects don't really have names. You can't open a file object by name. You can open a file, which is a different thing, and you'll get a new file object representing your connection to that file or device. But this is not about names at all. So file objects don't really have names, but ProcExplorer shows file objects here as though they have names because it is, of course, very convenient and very nice thing to see that I can know which handle points to which actual file. So this is definitely convenient, but it's not really a name for the object. Another feature of ProcExplorer is the ability to find. You can use Control-Shift-F to open this dialog for performing search, and it says handle or DLL substring. That really it means any kind of named objects as names as ProcExplorer sees them. So if I write something, part of a name or whatever that may be, we might be able to find something. So I can do something, maybe Explorer. So Explorer could be related to DLL names, could be related to mutexes that have the name, the string Explorer somewhere there. So you can see everything that has this Explorer thing searched throughout the system. And then, of course, we can, we can cancel the search if we have too much too many items anyway. In any case, we can click any one of these entries and we jump to the process and the handle that this thing represents. So the search is really about named objects, including naming as far as ProcExp is concerned, which means file names as well. So one very classic case where this is useful is when you're trying to delete some file and that file fails to delete because someone is holding that file. And so ProcExp can allow you with that search option to quickly locate the processes or process that has an open handle to the file, which is why you can't delete the file. And then you can just close the handle if you wish, or terminate the process, and then you'll be able to delete that file. And so if you right-click here, you can actually close the handle. Normally, I don't recommend it, but if you know what you're doing, you can do that. You can close the handle behind the process back. So this is, again, something that you can't do very easily. So the close handle API that some of you are probably familiar with can only close the handle in the current process. But in fact, there is a way to close in a handle in another process using the duplicate handle API with the flag duplicate close source. And that's kind of the way ProcExp does it in order to actually close a handle in a different process. Usually, this is very dangerous in a sense because the other process would get its handle kind of gone away without it even noticing it. So this is ProcExp, some of the aspects of ProcExp. Of course, there are many other things I could talk about, but we only have 30 minutes and my 30 minutes are almost up. Thank you very much. I hope you enjoy ProcExp. I hope you enjoy the new features, and hopefully we'll continue to evolve ProcExp even further and other tools as well, of course. Oh, one last thing. If you're like me and you like something darker than these bright colors, you can use options, theme, and switch ProcExp to a dark theme, which is, of course, a new feature in ProcExp that I hope you like.